It is really a great pleasure to introduce someone who is a coworker, colleague, collaborator, and a very good friend, Professor Dr. Karin Zonneveld, who has driven here from her research institute, MARUM, the Zentrum für Marine-Umweltwissenschaften, the University of Bremen in Germany. She is a scholar and a sailor who is a globally recognized expert on oceanography, the study of marine cores to understand the Earth system and its history. She studies climate change, both past and present. She leads an enormous research group, and part of her research really is ocean exploration, and she regularly is leading expeditions to extract cores from the bottom of the ocean. She is one of my favorite people that I've ever collaborated with. My only complaint is she always has the perfect excuse not to respond to emails. She'll respond to an email 3 weeks later and say, "Oh, I'm sorry, I was in the middle of the Atlantic Ocean," which is probably usually true, but it is a good excuse. So she's an adventurer and a scientist and a leader and expert on little organisms called dinoflagellates that she is going to talk about. Just last month, or early this month?
Last month.
Last month, about a month ago, the fruit of a collaboration was published. I've showed the core many times throughout the course, but haven't gone into great depth on the science behind it because I knew that Karin would be joining us. So this will be a treat for me as well as you, I hope. So join me in giving a warm welcome to Karin Zonneveld.
Yeah, thank you very much for inviting me. Welcome everybody. So I'm not going to talk that much about history. I'm going to tell you how we came to get such a core. But first of all, and a little bit about getting the link to the present. So the title of the core, I'm sorry I don't speak French. I speak French a very little bit, but not enough to give a talk. If I'm going too fast, just wave your hand and I will slow down. That's, I think, the most easiest trick we can do. So if you can't follow me, don't hesitate. I don't mind. Then I slow off and I will talk a little bit slower. I hope my sheets will explain quite a lot. So I try to put a lot of pictures in there so that you can follow me. If not, just say. So the title is, Did Climate Change Affect the Romans? Well, that's the specialist sitting there. But I'm going to tell more about what can the seafloor tell us. And this was a cooperation with actually more people working in the labs helping me, but these were the people of the co-authors on the paper. So first, where I'm coming from? I'm coming from the University of Bremen. It's laying in the north of Germany, although the Germans wouldn't say it isn't the north, it is somewhere in the north middle. It looks like this, and we are a marine institute going often to the ocean to collect ocean floor sediments. And we have a big core depository of marine archives. What they are, I will explain to you. And this is me standing in one of our labs working on one of those cores. So, but what we have now is, we have a big question. And that is, does the current climate change enhance the risk of pandemics? We know we have climate change, and these are just a few pictures of messages from last year. So we have extreme temperatures, and we had a COVID pandemic. So this is a question which is really very actual at the moment. And we indeed have climate change, and we can measure temperature changes, for instance, on the world, but that can also be biased a little bit. So the best thing is to look from a satellite to the ocean, to the whole world, and see if the temperature on the world is really changing. And these are satellite data from every month. Satellites started to measure in 1979. Before that, we didn't have satellites going around the Earth. And you see that indeed, if you look at the whole world, that we have an increase in temperature over time. Oh, sorry. the wrong one. So, and we are there now, and you see that it is really at the moment quite dramatic. We have an El Nino heating up the ocean. The Atlantic Ocean is very warm. But indeed, it's not only that it is in the papers written, we have the warmest year. You can also see it from space to the world. Now, does this make us more riskful too? Well, there maybe the past can learn us something, like what work Kyle is doing, trying to figure out those mechanisms. And this is one of his slides, and we've done that in the Roman time, in antiquity. As we saw already, there were crises, there were pandemics, and we wanted to know if there maybe is a link between climate and these historical things. But how do you come? We didn't have a thermometer, the Romans didn't have a thermometer, so they couldn't measure temperature. So how do we do that? Well, a little bit about the history. What we know of is some historical facts. We know that the Roman Empire expanded and that we had a decline afterwards. So this is the summary from what Kyle has already presented, very broadly, very quickly. Expansion in the past, and then we had 3 big pandemics over time. One in about 165, the next one where he was just talking about, and then one, the pest, bubonic plague, at the end in the years halfway to 500-600s. And also at the end the decline of the Western Empire. So, but how can we find information from climate in the past? Well, therefore, we take a ship. First, you can go to historic sources. For instance, this image of Hannibal crossing the Alps. We knew that if you had to cross the Alps had to be quite free of ice. So we know that it probably was warmer than it was now, maybe, as if there was less ice, less glaciers. But those historical sources are most not very precise. And if we write in our diary, we write the extremes. For instance, now, if there is snow, like this year, there is snow, then we write in our diary there is snow. But if somebody reads that 1,000 years later and thinks, oh, there was a lot of snow, but we have a very warm winter this year. So historical sources are good, but you always, and that's where you much more specialized in than I am, you have to take them with care. And I'm a natural scientist. I would like to measure things, but we can't go into the past. We don't have a time machine. So we use marine cores, marine archives. And how do these archives work? Well, think you are in an ocean and you have a nice big water column and an ocean floor. And in the top of the ocean, there's a lot of life living, for instance, plankton. At a certain moment, if that plankton dies, it falls down to the ocean floor. And there it can fossilize. So now, if something is changing there, for instance, this was a situation with cold water. If we get warm water, we of course get a different association there. Like, for instance, if you go on land, if you find a polar bear fossilized, you know it must have been cold. If you find a palm tree and it is fossilized, you know it must have been warm. So the same is the ocean floor. If these dies and fossilize, and you take part of the ocean floor out of it, you can read it like a book. You know, here it was cold, here I had my plankton polar bears, and here I had my plankton palm trees. So then you can reconstruct, and we call it reconstruction, we can reconstruct what was there before we can measure. And we call this a proxy. So then we have a book. We have a piece of ocean floor, but then we have to read it. And if you read a book, you would like to know what are the page numbers. So you must know actually the age, when was it settled down. We also want to have all the pages, so not that something is lost in between. If you lose a chapter, it's not nice reading. You also don't want to have them mixed. So you can imagine that if there are animals living in the ocean floor, mixing those things, like worms, for instance, mixing all those sediments around, you get a bunch of pages, but they are not in the right following up. So you want to have actually situations in the ocean floor where that didn't happen, where you have very nicely all the pages online, on the same pile, but not mixed up, with no mistakes. You also want to know, you want to find, you must be in an area where climate is changing, because if you do that in the middle of the Sahara, if you drill there, it would probably have been warm for a very long time. Plus what you want to do is you want to have a signal which is understandable. So the example I just gave with plankton, you must know which plankton is responsible for cold situations or warm situations. So these archives, where we have that, are worldwide extremely rare, because especially the mixing up. The last thing what you want to do, if you want to compare with historical data, you must have a very high temporal resolution. And think of that plankton going down in the ocean, in the middle of the Atlantic Ocean. It takes about 1,000 years to have only 1 centimeter of sediments. So we want to have that much faster, because we want to read a book. 1 centimeter, if you have 1,000 years in 1 page, you can't compare with history. So, but there are a few sites in the world where sedimentation goes so fast that you can really go down to having a signal every couple of years. And one of those real unique regions is happily in Italy. And the good thing of Italy is we have a very long historical record, and we have these archives. And the archive I'm going to talk about is laying here, just around the southern tip of Italy, in an area which is called the Gulf of Taranto. And if you see Italy, you have here the Alps. In the middle you have a mountain range, the Apennines. And if you look in the ocean on this satellite image, you see here some green, fluffy things. What is that? That is from satellite in the image taken, that is sediment, which is floating in the water. And if you look carefully, you see that's here very blue, nice blue water, but that sediments are floating around here, just around the coast. How does that come? Well, first of all, we have in Italy a couple of river systems. One big one, the Po River, draining the southern part of the Alps and the northern part of the Apennines, and local rivers. And these all bring fresh water plus erosional products into the ocean. And we have an ocean current system which presses this plume of fresh water. Fresh water is lighter than salt water. It's pressing this against the coast, and it goes completely around until there, and here it mixes with the rest of the seawater. So this is at the end of this plume of a river. So if we have more rain in the Alps or in the Apennines, you get more of this fresh water. So at this core position, you get then more discharge water of those rivers. So here, at that end, all the small little particles fell out, and they fell out very quickly, and we have a deposition of particles of about 1 centimeter, takes about 10 years to deposit. So if we have a lot of rain in autumn, or meltwater in spring, we get here a lot of little particles. These particles not only contain sediment particles, but also contain nutrients, which are feeding algae. So the algae, where I will come later on, they live on these nutrients, and they are mostly there in spring and in autumn. But how is the rain in Italy actually organized? And therefore I have to jump a little bit to a climate system. And the major climate forcing mechanism for rain in Italy is what we call the North Atlantic Oscillation. I'm not going to have detailed about how this exactly functions, but what you can know it is it's formed because of the high and low pressure areas in the Atlantic, which steer it. If these are very strong, we have a jet stream. This is a winter situation. In winter, we have a jet stream with a lot of low pressure areas going straight over the Atlantic. actually the situation which we have now, we get one after the other those low pressure areas with a lot of rain. So at the moment we are in a positive mode of this North Atlantic Oscillation. When these high and low pressure areas are not that strong, you get a much more meandering of that jet stream. And then we get a situation that the low pressure areas go a little bit more south over the Mediterranean. So at the moment we are in this situation, we get here a lot of rain, it is relatively warm in winter, but we have quite dry and cold conditions in the Mediterranean. So you hear now also in the journals, in the papers, it's written Spain is very dry, Italy is very dry. And we in Germany had floodings, you in France here had a lot of flooding. So this is also, if you go now to Italy, we have here the Alpine mountain range. If we have a positive mode of the North Atlantic Oscillation, a lot of rain is falling north of the Alps. If we have a negative mode, a lot of rain is falling south of the Alps. And this will have, of course, influence on the amount of rain or amount of discharge of the rivers in Italy. So how to collect the marine core? Therefore we take a ship. And this is one of my favorite German research ships. You have the Marion de Fresnes, also a very beautiful ship, but I must admit better food than we have on the German ones. So, and a glass of wine during lunch, which we don't have. But this is also a nice ship. You take a ship. And then we go to collect the core, if it wants to go on. How do you collect the core? Well, first you go to the region where you want to go to, and first you have to scan the ocean floor to see what is the perfect position for such a marine archive. And this is a picture of my colleague. He's in the Mollenhauer in front of screens. We measure with sonar in the ocean floor. You see here very nice, it reacts on the density in the ocean floor. You see here very nice lines. So here you don't see any mixing up, no disturbance. So that means a very nice position to take those cores, to let them read like a book. Then you're going to really collect those cores, and we do that with these two machines. The first is called a multicorer, where we have very small cores. This will be set on the ocean floor. Then we let it sink into the ocean floor. There are little caps here which close it. Then it comes up and you have a very small archive. But it's not going very deep. If we want to go further back in time, we need something stronger, and that is this. This is called a swirload or a gravity corer. On top of it, we will see it later on a little better, there is about 2 tons of weight, a very long tube, and in this tube we have a plastic tube which we can take out afterwards, and a closing up. So how does it look if it goes into the ocean? It's on a wire, we let it suck down, here is the tube, and this is the weight on top of it so that it can sink into the ocean floor. And here am I with my colleague getting that inside tube out, and we're going to cut it into pieces. Well, to have you a little bit idea how it is working, I have here a little film sorry that it is moving. Everything on the ship is moving because we are on sea, so you see also the horizon. If you're getting ill from it, just look at the other side. But you see here Gerard, my colleague, cutting the core, getting it out. Lids are being taken up because you can't get that whole 8-meter core, you can't have it in once, so we cut it in pieces. But this was in the morning very early. You see we work in all weather, we work during the day and during the night. The next one, afterwards, when the core is taken, we bring it to the dry place inside the ship, and in the ship we lay them out. We make them dry. The ocean floor is mostly only 4 degrees Celsius, so as soon as it's coming on deck, it's immediately getting wet, and we dry them. But we also mark very carefully already outside. We mark what is the top of the core and what is the bottom of the core. Very important, because you know if you cut it into pieces that you must have the pieces once after the other. So we do that, as you see here, very systematically. The first one is laying far away, and then we fill it up so that we immediately mark them outside. What is the bottom? but then we mark it with at all sides very carefully. Then we cut the core into half, and it looks like a cutted core looks like this. You see, we nicely marked which one is what, and you can see here already those little lines. So this is the bottom, and this is the top. So this is deposited first, and you see here already those little layers of sediment. Yeah, and if you take such a little layer out and analyze it, and analyze what is in it, you get a signal from the past. So this is then ready to be read, ready to be subsampled and analyzed. And of course, afterwards, you take a break. So this is when it was really light, and you see, yeah, we don't mind. At a certain moment, you get used to. So Carl once said that he wanted to join a ship cruise. You still want? Good, but then how to read such an archive? That's the second step. So I said you need to have the page numbers. So how are you going to get page numbers? Well, here again, in Italy, we have a unique situation. We have measurements to do that with isotopes, C14 for instance, but they always have a little bit an error of about 100 years. So for historical work, that's not really very practical. What we have here in Italy is the good situation is that we have in the vicinity, we have volcanoes. And here is the Vesuv laying, here's the core, here's the Vesuv laying. We have here a couple of islands, the Lipari Islands. And this is for us, a very important island, the island Lipari. But yeah, if you think of a volcano, when there's an outbreak, there's a lot of ash coming into the atmosphere. And in that ash is not only pume, but also there are also little glass particles. And the little glass particles, they have in their elemental signal, a signal which is unique for every volcano, and even unique for several outbreaks. So, what did we do? We looked into the core, and we looked through the microscope to the particles in there, and looked to, well, these little ones. This is with polarized microscopy, an image taken. And you see here a little glass particle with very little holes in it, and that is because there is in such an outbreak, you get glasses very quickly made, and there's a lot of gas in there. So that's why you get particles which are very well recognizable, but they are very small. So we have to sieve the material, then have a look under the microscope and count how much of these particles we find in a certain fraction of sediment. That's what we've done. So we have taken about 800 samples, no, 600 samples, and counted how much of these glass particles were in there. And this came out. So we had certain layers where we found a little bit more of those particles. So that means here there must have been ashes deposited in the core, here as well, here as well, and here as well. Then we analyzed the elemental composition of these particles. So we had to pick them out hand by hand. So how do you do that? You take an eyelash, put it on a needle, made it a little bit wet, and you can pick them out one after each other, put them on double-sided tape, put a resin on it, made it very, very flat, and then we can measure it with a beam in high vacuum. And then you can get the elemental signal. The elemental signal means how much kalium, how much natrium, how much magnesium, how much iron, and so on. And here I only have a few ones which are measured in different colors, and we have here silicium amount, and here, oh, that one fell away, but it's natrium-kalium amount at the other axis. And these colors represent the typical signals of different volcanoes. For instance, Hellenic arc. We have here, the pink one is the Vesuvius. So all particles which are coming out of the Vesuvius, if you would have a Vesuvical particle, it would lay on this curve in these pink areas. And we see that we have indeed a few particles which fall in there. But most of them fall here. And this is typical for that island Lipari, from the Lipari Islands. And now we can play with it and say, okay, where they're really coming from. Well, happily, other colleagues, which were working also in the Gulf of Tarrant, found out that several of these, that we had a mixture of outbreaks which were very well known from the Lipari and could put dates on it. So we could date particles in these ashes. For instance, this one was a Lipari volcano, but we also found one typical glass chart for the outbreak of the Vesuvius in 79 after Christ. Very well known, the most famous outbreak actually, which is known. We have another particle of the Vesuvius, which is typical for an outbreak in 512, and an outbreak of the Monte Pilato, the big mountain on the Lipari Islands. So now we have exact dates in our core. So we have exact page numbers. And we can interpolate then the age in between these page numbers. How do we do that? We call that an age depth curve. So here is the age, and here is the depth in the core. We have those three marks, and we had also 14C dates. I'm not going into detail about those. They are not that precise, but we have those three precise ones. We make a curve around it, and now if we have a certain depth in the core, we can read what age it is. So now we have from every sample, we have our age, your page number. Good. So we have our archive, we have our page numbers, but now we must have a tool how to come to climate. How can we say something about temperature and precipitation? And that is what Carl already said. I used for that plankton organisms, marine dinoflagellates. And they are plankton living in the upper ocean. And in the life cycle, they made cysts, which are not motile, so they sink to the bottom. They are fossilizable, so they also stay fossilized in the ocean floor. And every species has a cyst which looks different. So the morphology is species specific. And these we can extract out of those subsamples we have taken. We count then how much of every species is there. And then we have countings of which species were there in the past. This group of organisms is very sensible for changes in environment. It might be that you have been to the sea and have seen the sea lightning, the blue lights in a very beautiful summer day, that sea is illuminating. There are also these organisms which are doing that. So, but also if you pollute the ocean, we get often, you've probably heard of toxic blooms because of a lot of ocean pollution. That is also these organisms. So the association of these organisms react on changing in environment, in the ocean, in the water. So we have species which are typically there in relatively warm areas. So this is a global data set, and we looked where the different species are coming from. So this one you won't find in the Arctic. You find them in the Mediterranean, but not very much far up. Other ones, like this one, you only find in colder waters. And you see that the Mediterranean is its outer rim. So we had a set of species which are warm and they're cold. And if we make a ratio between them, if we have a little bit more of these ones, we know it must have been colder. If we have a little bit more of these ones, we know it must have been warmer. And that's exactly what we did. What we also did is, well, we wanted to look in this plume, what kind of species were typically for this plume. Because if you would have more of these species here, then it means that there is more plume water coming here. If you have less, then the plume water probably didn't reach this side. So we went with the ship, and all those yellow dots are small cores which we took with different cruises. We analyzed which species were in there, and we could analyze very beautifully the difference between what you see here in this plume around Italy and which was there in the open water. And we had a certain amount of species which were typically there, like this one, in the plume, and were not there in the open water. So pink is there, is that it is 0, it's not there. red is when it's very common. Well, why are you going to? So, we have then a temperature tool, proxy, that is the difference between those warm and cold species. And we have a tool, we have a group of species which are typically for river discharge. And now we can make a reconstruction, now we can play with it. But then it is also, yeah, you can look at it in the modern, but is this really reliable? Was this also the same situation in the past? You first have to check that. So, because we know at the moment, you can go down to the ocean, but we know we pollute the ocean. We know that the Po River is a very dirty river. So, is this situation which we find now representative for something like a Roman time, where there was no industry in the Po Valley? And this little bit history, you can do it much better, but these two persons are very important for us to check that. Because the first one, the Grand Duke de Medici, he was living in the same time as when the thermometer was invented. Do you know when the thermometer was invented? You're a historian. Do they know that? Somebody knows? No? What? Yes, Galilei. Somebody knows. And the other one, I will come later to that person. He lived a little bit later. But first we go to the Grand Duke, when this goes on. He lived there in Italy, and he lived at the same time as Galilei, and Galilei invented the thermometer. His students made it better, but the Grand Duke was very much fascinated by nature, and he was very much fascinated by measuring nature. So what he did is he let those thermometers, those first thermometers which were made by the students of Galileo, made 30 of them and distributed them to all the monasteries in his area, but also to Berlin and also to the Pope. The Pope said, no, you have to stop measuring nature because nature is from God. You are not allowed to measure it. But he found himself, I think, you never know, better as Galilei, because in his monasteries, temperature was measured every time the monks went to pray. They had to put in one of those thermometers on the north face, one on the south face, and every time they had a prayer, they had to measure what kind of temperature it was. Well, these things are glass-made, handmade, little glass jars, and they are filled with brandy with 85% alcohol. These dots here, these measures, are done by hand, but they are very exact. So the minus, they put it in melting snow. The plus was in June in the Arbo. Arbo, what was it? Arno, sorry. In June in the Arno. I always have a problem with the Arno. I don't know why. It's but well, there was one historian colleague, Camuffo, and he found those thermometers back in a museum and could trace them from which monastery they came. So he visited all those monasteries. He calibrated these old thermometers with a modern one. He went to the archives in those monasteries, and he could say then what was the real temperature at that time. The second one was the royal emperor of something. He was actually living in Venice, and Italy was first. There were first the dogs in Venice, but when the French took over northern Italy, they wanted to have an important person there and put that guy there, and he was much more. He found himself much more civilized and was also much more organizing things. And what he knew that in Venice they had a problem with flooding. So every so now and then, Venice got flooded. And he was very clever. He said, okay, I put somebody here 1 water day travel away from Venice and let somebody measure the levels of the river of the Po every day. So, or twice a day. And that was first sent with pigeon to Venice, so that they knew one day in advance we will get, the level is rising, we will get a flooding, we can prepare on that. This record is started in 1818, it stopped in 1984. Do you know what was happening in 1984? Somebody? Political. Berlusconi came as becoming the president. So it's not only Trump who's doing troubles. Berlusconi also thought, no, nature that costs a lot of money, scientists cost a lot of money. A stupid guy measuring every day the water level there, why do we need it? We have satellites, we don't need it anymore. So the record is stopped, unfortunately. But for us, we have a very nice record, daily record, and we can tune our proxy to these records. So these are these records. The upper one is the one of Camufo. Unfortunately, Camufo didn't publish his daily data. He only published an anomaly, and the anomaly is that he took the mean between the years 1960 and 1990 and said everything which is warmer, a certain amount of degrees warmer, we put it in red, a certain amount of degrees, temperatures colder in blue. And he made a graph and he said data are stored somewhere. Unfortunately, his data got lost. He retired, his computer was thrown away, his hard disks were thrown away, and the original data, which he took years to gather, they're maybe somewhere in Italy, but nobody can find them. So at least also in Hamburg, in the Climate Center, they're desperately looking for those data. And they might turn up in future, but we only have this graph. These are data from, the upper are the data from Sanchetti. It's the daily curve of river output, and he had, after 1985, he had several extra measurements done by himself. So if we put our core on top of it, well, you see that the fit is not that bad. So the black one is, you see that it is following more or less Camufo, and especially here, it is following very beautiful the river discharge of the Po. I couldn't do it in this period because there I saw that my association was so changing that I only had polluting species in there after 1910, after in the Industrial Revolution. Then waters got so polluted that only before that I could see a pure river signal. Afterward, I only got a pollution signal. There's another record, and that is published not very long ago in 2017. And that is a record from the year 6050 to 2010. And the light blue is the instrumental record, and the black one is our record, and this fits really quite well. So we can say, I think our tool works. So finally we go to Roman times. And then this curve you've seen more often, what came out. We saw that it was we had a lot of warm water species, and then suddenly you get a change to colder ones. We also hear, so now you see plateaus. That is because we don't find cold water species. So then we don't know how warm it was, but we know at least it was warmer than that the cold water species couldn't live there at all. So, but from here we have both, and then we see a lot of variation, and then another drop there. So we see that it's about, at least in the first part of the Roman time, that it was warmer as today. It's also fit with what is known from historical records. And then it's getting colder. Oh, sorry, there's a 5 too much. That 5 must be gone. It's the year 130. What we see there, that it is that the temperature drops below the variance we saw in the couple of years before. So we see here a variance in temperature, but you see that here the curve really starts to go beyond that. So the Romans, here, yeah, temperature might change, but they didn't notice that much. But here they must have started to notice something. So we have actually 3 strong drops, And then so now then the warmings again, at least this one, here another one, and we have another strong one here, and in between here, temperature remains fluctuating quite much. We also, of course, tuned it on what other people did. I'm not going to show that, but it fits quite well, and that is what Kai so now and then showed as well. River, what did that do? Well, we see actually quite variation, not that much. The only trend we see a little bit is here, that we see here, especially going to the third century crisis, we see that it's getting drier in Italy. So, some conclusions about the climate. It was stable until the year 100, and then it started to get colder, but only after the year 130, then it really gets out of the range what you've seen before. We have three main cooling phases, it's getting unstable and cold after 500. And then the one which Carl often shows, now we can compare it with history. So now you have those climate curves. You can compare it with history. We could compare it. We saw that the pandemics fall in those phases when climate has changed, so in the cold phase. But you see that it's not immediately happening directly after things happen. There's a phase lag in between. Why? As Carl explained, it's very, very, very complex. But what we know is that climate correlates to Roman history. Epidemics and pandemics we find in the cooling cold phases, and that the pandemics follow the climate. So it's not that we first have a pandemic and then climate changes. You could also think of that. For instance, if you have a pandemic, half of your population dies, there's less fuel being burned, less CO2 in the atmosphere, then climate would change. It would also be a logical idea, which has been proposed in the past. But it was very quickly known that that is not the case, and we also see that the pandemics follow climate change and it's not opposite around. So, the last big question, can this be causal? And that is where the whole whole lectures of Carl are about. Well, I'm not a historian, I'm not a medical person, but yeah, we know that Rome there were many people, and they might have been on the edge of their existence, what the country could give them. We know that they had very good road networks. And if we make the comparison to us, we also have a big population, which is more or less at the moment on the population size on the existence level. We have excellent transportation modes. We saw that with COVID. It goes quickly all over the world. Our lifestyle is actually adapted to a quite stable climate. And you see also now there is a warming. We had those images of warming, the warmest year. We're not changing our lifestyle at the moment. We just hold out and say, okay, next year will probably be better or maybe not. So we only get a problem. We are quite resilient. We will start to grow other crops when it's really getting necessary. But still, climate is influencing basic factors which cause our well-being. So, for instance, where is rainfall, where we have fresh water, or agriculture. There's a lot of things which climate still, although we are in another stage, completely other stage as the Romans, but climate is still fundamentally influencing basic well-being processes in our life. But, so, yeah, and this is a question, does our current climate change enhance the risk of future pandemics? I can't answer that question. But we have modern science, and the good thing is, and I quote you now, I really love that quote he gave when we were talking with journalists about our paper. He said, with everything that comes with it, we know now we have germ theory, we know where the diseases come from, we know of spreading. Climate is changing the habitats of species, but also of germs. So we see that species are moving now over the world because of the climate change. But we know that, and we can monitor that, and we have vaccines, and we have medicine. So we are much better off than the Romans were at the time. So, and we scientists, and I think that's one of our major tasks, is showing all around the world we have to become sustainable and give it the tools to become sustainable. And that's where I wanted to end. So, sorry I can't answer the question. I can imagine that we are, but I don't know. At least I know that climate is still important, and it might be underestimated by most of the people, so that they say, you know, we can handle it. I'm myself not that sure about it. I think we have to take it seriously. And, but the only thing we can do is going on with combining things like this, trying to find out in the past, what were the mechanisms in the past, do they also hold now for the future? At least we learned from it, and from that we can say, okay, we can prepare ourselves for the future. And I put this one on, so again for you, if you want to go to see a little bit of an image of how beautiful our ocean actually is, and the waves. So, for me, if there are questions, you're very welcome to ask them. Let's